Corsets. Let me recall the definition of corsets that you have done in third semester. Let H be a subgroup of G under the binary operation dot. Then for any A belong to G, AH is defined as set AHI such that HI belong to A. That means A capital H contain all those elements of the form AHI, where you have to multiply A from the left side of H, and HI is an element of H. This is called the left corset, and the right corset is defined as HA such that it contained elements of the form HI into A. Now note, if G is a group under the binary operation, instead of that the binary operation is plus, then in that case the left corset is defined as A plus H, which is equal to set A plus HI, where HI belong to H, and H plus A is defined as right corset, and it contained the elements of the form HI plus A such that HI belong to H. Now index of a group. Index of a group, a subgroup in a group is defined in this way. Let H be a subgroup of G, where G is a finite group. That means G contains only a finite number of elements. So H also must be finite. So we know that any two right or left corsets of H in G are either distinct or identical. For example, suppose HA and HB are the right corsets of H in G. Then either HA intersection HB is equal to phi, that is empty, that means they are distinct, or HA is exactly equal to HB. So that is the meaning of this one. The right corsets of H in G are either distinct or identical. The number of distinct right corsets of H in G is called as the index of H in G. So this is definition of index. The number of distinct right corsets of H in G, or the number of distinct left corsets of H in G, is called index of H in G. Note that if there are n distinct right corsets of H in G, then the number of distinct left corsets of H in G also will be n. Now let us come to this theorem. If H is a subgroup of index 2 in a group G, then H is normal in G. That means if there are only two distinct right corsets of H in G, or distinct left corsets of H in G is 2, then H must be normal in G. So proof, given index of H in G is 2. So the number of distinct left or the number of distinct right corsets of H in G must be 2. Now let us take an element X belong to G, be an arbitrary element of G. Then either this X belongs to H, that subgroup, or X does not belong to H. So let us see case 1. If X belong to H, then in that case, XH is equal to HX is equal to H. This is by the theorem that you have done again in third semester. If H is a subgroup of G, then H into H is equal to H into capital H is equal to H for every H belong to H. That means if you multiply this subgroup H on the left or on the right by an element that belong to H itself, then it will be that group H itself. So here, since X belong to H, so by this theorem we have XH is equal to HX is equal to H. And this by the first theorem on normal subgroup, we can conclude that H is normal in G, because H is a normal subgroup if and XH is equal to HX. That is the first term that I have already proved regarding first term on normal subgroups. Okay, so by applying that first term, we can conclude that H is normal in G. Now let us come to case 2. In case if X does not belong to H, then in that case, what are the two distinct left corset or distinct right corsets of H in G? Since it is given to be 2 only, then XH and EH where E is identity equal to H itself, this will be the only two distinct left corsets of H in G, because it's given that index of H in G is 2. And since G is equal to X, these are the two distinct left corsets. So G must be the union of these two distinct left corsets. This also by the theorem on corsets. Again, these things you please go through again the notes of your third semester, so that you'll be more clear with this one, because here I don't need to prove all those theorem again. Just the application of those theorems are needed. So if you remember the statement, then you can apply it in the proof of the theorem on normal subgroups. Let G be a finite group and A1H, A2H dash dash A and H be n distinct left corsets of H in G. then in that case G will be the union of all these distinct left corsets, or it is the union of all the distinct right corsets. So here by applying this theorem, I can, since there are only two distinct left corsets, so G must be the union of XH and H. Also, as X does not belong to H, so HX and HE, which is equal to H, this will be the two distinct right corsets of H in G, because again the index of H in G is 2. That means the number of distinct right corsets also will be 2. Again, by this theorem, G must be equal to the union of HX and H. So XH union H is equal to HX union H. So from here, this is equation 1 and this is equation 2. G is the union of XH union H, and also from 2 HX union H. So these two must be equal. So now XH intersection H, because these are the distinct left corsets, so this intersection of this must be equal to 5. So which means that the element XH will be all those elements of G which are not in H. So XH must contain those elements of a group G which are not in H, because XH and H are distinct. And similarly, HX will be equal to G minus H. So this implies that XH is equal to HX. And by the first term or normal subgroup, we can, since XH is equal to HX, so this will imply that H is normal in G. So I hope now it's clear regarding the proof of this theorem. You'll see that later on you apply this theorem in solving the problems. That is, if we can show that the index of that subgroup in G is 2, then we need not prove, that H is normal in G by using the definition. Straight away, by the statement of this theorem only, we can conclude that the given subgroup is normal in G.